Welcome to our new video on the MIT 2024 Integration B Finals. We'll look at the main questions. We had question number 1, question number 2, question number 3, question number 4, and question number 5. Then the session progressed into a tiebreaker series, which also had question number 1, question number 2, question number 3, question number 4, and question number 5. After then, things were still tied, so they had to progress into the lightning round, which consisted of question number 1, question number 2, and question number 3. It was only then that the winner was declared. So I'd like to really encourage you to continue watching. It's I think a great series consisting of these very great questions. If you haven't subscribed to our channel, we do really encourage you to consider subscribing to our channel. Your subscription and your liking of our video would help us get that extra visibility. That will bring some more traffic towards our channel. So other than that, let's go ahead and solve these problems one by one. This is problem number 1 of the MIT 2024 Integration B Finals, which is the indefinite integral of e to the power x over 2 times cosine of x over cube root of 3 cosine x plus 4 sine x.
Problem here is interesting, and one thing that I personally would consider is looking at the denominator and see that there should be a derivative of 3 cosine x plus 4 sine x to the power 1 over 3 plus 1. And then that has to be combined with the derivative of e to the power x over 2. So it's a product of the function 3 cosine x plus 4 sine x to the power 2 over 3 and the e to the power x over 2. And one thing that needs to be obviously figured out is the constant. It's the constant k that needs to be figured out. So that when you consider the product, the derivative of the product of this to the power 2 over 3 and this, it should be okay. So I'm trying to figure out the product k, so that when I get the derivative of this, which is this, times the derivative times this, when I get the product of this and this and then get the derivative, I should multiply with that constant and should actually get what is inside this integral sign on the left hand side. When I keep this constant here and have this derivative here plus this times the derivative of e to the power x over 2, I should ideally get whatever is on the left hand side. So k, and then we have e to the power x over 2 times the derivative of this plus the derivative of x over 2, which is e to the power x over 2 over 2. That should be equal to whatever is on the left hand side. So then, as you know, we keep maintaining our constant there as shown here. So with k there and then combining everything together, you see the sine terms cancel out, and then we're left with 8 over 3 cosine x plus 3 over 2 cosine x, right? So that becomes e to the power x over 2, 25 over 6 cosine x over the cube root of 3 cosine x plus 4 sine x. Now we see that we have this constant 25 over 6 that needs to be negated so that the left and the right should be equal, and that is when k equals to 6 over 25, right? So when k is equal to 6 over 25, both the left hand and the right hand sides are equal, and that means that for our integral here, it means that it's 6 over 25 times the integral of the derivative of 3 cosine x plus 4 sine x to the power 2 over 3 and e to the power x over 2, right? As you can see. So the answer therefore obviously is 6 over 25. When you integrate this derivative, we get 6 over 25 times e to the power x over 2 times 3 cosine x plus 4 sine x to the power 2 over 3 plus the integration constant. And that, our friends or my friends, is the answer.
So on to problem number 2 of the MIT 2024 integration B finals is the integral from x equals to 0 to x tending to infinity of the natural logarithm of 2 times e to the power x minus 1 all over e to the power x minus 1.
So the first thing that one would do is to let u be equal to the natural logarithm of 2 times e to the power x minus 1. And so e to the power u is equals to 2e to the power x minus 1, and therefore eu du dx is equals to 2e to the power x. And so e to the power u over 2 to the power e over 2 times e to the power x du is equals to dx. And since we know 2e to the power x is the same as e to the power u plus 1, so therefore e to the power u over e to the power u plus 1 du is equals to dx. And so when x is equals to 0, 2ex is equals to 2, and therefore 2 minus 1 is 1, natural logarithm of 1 is 0, and when x tends to infinity, u tends to infinity, so we have 0 and infinity unchanged. And therefore, in place of log, natural logarithm 2e to the power x minus 1, we have u, and therefore in place of ex, we have eu plus 1 over 2 minus 1, and then we have eu over eu plus 1 du. So this goes up here, so we have 2, and in the denominator now we have eu in place of this eu minus 1, and so in the numerator we have u remain, and next here we have eu over eu plus 1. So we have a product of these two numbers. Then the next thing is we do now have our integral as shown here. One thing that we could do is obviously pull out u and e to the power u, and then now we have 1 over e u minus 1 minus 1 over eu plus 1, and then we pull out half because if you combine this back together you get a 2 in the numerator, so to cancel that 2 we have a 2 out here, so the 2's cancel out, and so we're left with u, and then if you divide both the numerator and denominator by e to the power u, we have 1 over 1 minus e to the power u minus 1 over 1 plus e to the power negative u. Now what is very obvious here is that we do have a geometric progression that is really standing out. So these are geometric progressions to infinity with a common ratio, e to the power negative u, and here negative e to the power negative u. So we have our geometric progression here as shown here, and we can pull the negative 1 to the power k here, so that we do have our nice expressions shown here. So the next thing we can do now is combine the constants So we have 1 minus negative 1 to the power k in bracket, and then e to the power negative k, the power u. So we can now swap the summation sign and the integration sign. So we have inside the summation sign the integral from 0 to infinity of u times e to the power negative k u. So what happens eventually is that we know that e to the power negative ku is the same as the derivative of 1 negative 1 over k times e to the power negative ku. So what we see here is that we can use integration by parts, and the integration by parts in essence means that when you have u, capital U and dv, the integration is uv minus the integral vu du. So since this is our dv, our uv is the same as u times 1 over k e to the power negative ku negative with the limits applied, plus 1 over k times the integral of e to the power negative ku. So when u tends to 0, let's begin with the upper limit. When u tends to infinity, this part tends to 0, so this entire thing goes to 0. When u tends to 0, this is 0, so this entire thing goes to 0. And so we are left with the integral of 1 over k, times e to the power negative ku. And this is also the same as 1 over k times 1 over k negative e to the power negative ku. And as you can see, when u tends to infinity, this tends to 0, minus when u tends to 0, this tends to 1, so we have plus 1 over k that is left here. And so our integral becomes the summation of 1 minus negative 1 to the power k times 1 over k squared. And that means that when k is even, this becomes positive 1 and this becomes 0. When k is odd, this becomes negative 1 and this entire formula becomes 2. So we are left with now what we say is 2 times 1 over 2k plus 1 squared. So only at odd values of k of the denominator is when we have this square taken into account. So that is that. We can pull 2 out, and then we're left with the summation of 1 over 2k plus 1 squared. So we can use the Basel problem to try and figure out what this summation amounts to. The Basel problem is if we have a summation of 1 over k squared, that from 1 to infinity, that adds up to pi squared over 6. So what about the odd terms? So since the even plus the odd terms adds up to this, these even terms can be reduced further by squaring the 2's separately with the k and then pulling their quarter out, and so we realize that this is still the Basel problem. So we have a quarter times pi squared over 6 plus the summation of the odd terms is equals to the square of pi over 6. And so this is pi squared over 24 plus the odd terms squared is equals to pi squared over 6. And so what the odd terms remains with is pi squared over 6 minus pi squared over 24, which is 3 pi squared over 24, divide 3 numerator and denominator, we have pi squared over 8. So the odd terms add up to pi squared over 8, and the even terms add up to pi squared over 24, right? So when we we know that our integral is twice the summation of the odd terms, 2k plus 1 squared, and so we plug pi squared over 8 in place of this sum, and that means that our answer is pi squared over 4. And that is the answer that was provided in the.
So problem number 3 of the MIT 2024 integration B finals is the definite integral from x tending negative infinity to x tending to positive infinity of 1 over x to the power 4 plus x to the power 3 plus x squared plus x plus 1. So solving this problem, first we're going to factorize the denominator of the integrand. So looking at x to the power 4, x cubed plus x squared plus x plus 1, the first thing I would like to do is, so if you have x squared plus a half x plus 1 squared, this is the same as x to the power 4 plus x cubed plus 1 plus 5 over 4 x squared plus x plus 1. And so x to the power 4 plus x cubed plus x squared plus x plus 1 is the same as x squared plus a half x plus 1 squared minus 5 over 4 x squared. Right? So that's one thing we can do. Then using the difference of 2 squared, x squared minus b squared being equal to a minus b bracket a plus times a plus b. So we can form this into this perfect square so that it looks like b. So this is the same as root of 5. So root of 5 over 2 squared, right? So we can go ahead and do that. So instead of, we just did that. Okay. And so now a minus b is going to be x squared plus a half x plus 1 minus root 5 over 2x. A plus b is x squared plus a half x plus 1 plus root 5 over 2x. Now I would like to collect the like terms together. So for example, the negative root 5 over 2x and then combine it to half x. So that becomes x squared plus 1 minus root 5 over 2x plus 1 times x squared plus 1 plus root 5 all over 2x plus 1. So now we've gotten to this very good step that we wanted ourselves to be. So we'll continue. So our integration now becomes, so the integration of 1 over x squared, x to the power 4 plus x squared cubed plus x squared plus 1 plus x plus 1 is the same as the integral from x tending to negative infinity to x tending to positive infinity of 1 over the product of x squared plus 1 minus root 5 over 2x plus 1 and x squared plus 1 plus root 5 over 2x plus 1. Now we can express this fraction that we have here into partial fraction or partial fractions as follows. Now, when expressing partial fractions, obviously we have a known constants that we're going to create, a, b, c, and d, such that the numerator is a polynomial 1 degree, um, and we assume it's a polynomial 1 degree less than the denominator. So we have to assume, and then we'll go ahead and derive what a, b, c, and d are. So when we multiply the left and the right hand side with the product of x squared plus 1 minus root 5 over 2x plus 1 and x squared plus 1 plus root 5 over 2x plus 1, and so we get on the right hand side 1, I mean on the left hand side 1, on the right hand side we get ax plus b times x squared plus 1 plus root 5 over 2x plus 1 plus cx plus d times x squared plus 1 minus root 5 over 2x plus 1. And then we continue expanding the product on the right hand side and collecting like terms together. We get a plus c x times x cubed plus 1 plus root 5 over 2a plus 1 minus root 5 over 2c plus b plus d, all times x squared, plus open brackets 1 plus root 5 over 2b plus 1 minus root 5 over 2d plus a plus c, all times x plus b plus d. So we got the expression 1 is equivalent to a plus c x cubed plus open bracket 1 plus root 5 over 2a plus 1 minus root 5 over 2c plus b plus d, or close bracket times x squared plus 1 plus root 5 over 2b plus 1 minus root 5 over 2d plus a plus c, close bracket times x plus b plus d as the constant. So as we can see, we have no x cubed term on the left hand side. So what that means is that a plus c equals to 0. Equally, since we have no x to the power 2 term uh, in the left hand side, on the left hand side, that means that this part here is also 0. 1 plus root 5 over 2a plus 1 minus root 5 over 2c plus b plus d equals to 0. And also, since we have no x term on the left hand side, that means that this term also equals to 0. So 1 plus root 5 over 2b plus 1 minus root 5 over 2d plus a plus c equals to 0. And then the only thing that's on the left hand side is 1. So this constant here is equals to 1. So b plus d equals to 1. Okay. And meaning that from the top here, it means that our c is equals to negative a. And then we can proceed since b plus d equals to 1. First of all, let's collect like terms here. So we have a plus c over 2, and then we have a minus c over 2 plus b plus d. And then here we have b plus d over 2, collecting like terms, and then root 5 times b minus d over 2 plus a plus c. And then from here we can see that d is the same as 1 minus b. So that's the first thing we can do. Now, seeing that b plus d equals to 1 here, and then a plus c is 0, so this goes to 0 here. Let me get this. So this is 0, and this is 1. And then since a minus c, c is equals to negative a, we get 2a here. And that results into 2 times this root 5 over 2a plus 1 equals to 0. Same thing here, since this is 1 coming from here, and then a plus c is 0, this is 0. And then since b minus d, since d is 1 minus b, so b minus, in bracket 1 minus b is the same as 2b minus 1. And so we have a half from here, 1 over 2 times plus root 5, open bracket, 2b minus 1 over 2. And since this is 0, so that is equals to 0. And so from here, we can clearly see that the 2's here cancel. And so root 5a equals to negative 1. And then we can now take this a half onto the other side. Or we just multiply across by 2. So we have 1 plus root 5 in bracket 2b minus 1 equals to 0. Since we found that root 5 times a is equals to negative 1, that means that a is therefore negative 1 over root 5. And also since c is equals to negative a, that means c is 1 over root 5 positive. Also equally, since we saw that 1 plus root 5 times 2b minus 1 equals to 0, now we can take 1 to the, we can subtract 1 on both sides, so we have 2b minus 1 root 1, and if we divide by root 5, we have 2b minus 1 equals negative 1 over root 5, and therefore 2b is the same as 1 minus 1 over root 5, and therefore b is the same as 1 minus 1 over root 5 over 2. Also, since d equals to 1 minus b, as we saw previously, that means that d is the same as 1 minus 1 over root 5 over 2. Make a common denominator for both, so we have 2 here, which makes this 2 minus 1 is 1, and then minus minus we have plus 1 over root 5. So d is the same as 1 plus 1 over root 5 over 2. The partial fractions that we're seeking to create is now attainable, since we know a, b, c, and d. A is negative 1 over root 5. B is the same as 1 minus 1 over root 5 over 2. C is the same as positive 1 over root 5. And D is the same as 1 plus 1 over root 5 over 2. So this is our partial fractions. The first is negative 1 over root 5 x plus 1 minus 1 over root 5 over 2 all over open bracket x squared plus 1 minus root 5 over 2x plus 1 plus 1 over root 5x plus 1 plus 1 over root 5 over 2 all over x squared plus 1 plus root 5 over 2x plus 1. So this is our partial fraction. And this now is going to make things easier for us to now integrate this problem. Now, since we have this partial fraction that we're looking for, now we can go ahead and solve this problem. Which means that our integral now becomes the integral of 1 over x to the power 4 plus x cubed plus x squared plus x plus 1 from x tending negative infinity to x tending to positive infinity now is same as the integral from x tending to negative infinity to x tending to positive infinity of negative 1 over root 5x plus 1 minus 1 over root 5 over 2 all over x squared plus 1 minus root 5 over 2x plus 1 plus 1 over root 5x plus 1 plus 1 over root 5 over 2 all over x squared plus 1 plus root 5 over 2x plus 1. So we can separate this into two separate integrals. The blue integral that deals with this first portion here, right? And then the green integral that deals with this second integral. So we're going to deal with these two integrals separately and then combine the results we get. So this is the new integration set we have. We have the blue and the green integrals. And then, so we're going to start and focus on the blue integral. Yeah. And let's focus on the denominator. If you have the polynomial, so let's look at this polynomial here. If you have the polynomial x squared plus bx plus c, this is the same as x, because we're trying to create a perfect square involving that denominator. This is the same as x plus b over 2 squared minus b squared over 2 squared, which is 4 plus c. So that's what we're going to try and do, because this is our b here. And so we're going to have 1 minus root 5 over 2, which is 1 minus root 5 over 4 plus x squared. That's what we're going to do here. Because let's deal with the blue integral first here. As we can see, what we've done is we have focused on the denominator, keeping the numerator as it is, and so we have x plus 1 minus root 5 over 4 squared minus 1 minus root 5 over 4 squared, then plus 1, right? So now 1 minus 5 over 4, 1 minus root 5 over 4 squared is the same as 1 minus root 2 root 5 plus 5 over 16. But then this is negative, so we have to subtract 1 minus this. I'm going to do that. So this eventually becomes 16 as our denominator, and then making this become 16 minus 5 plus 1 is 6, so minus 6, minus minus, so we have this becomes 2 plus 2 root 5, right? And this now becomes 10 plus this becomes 10 plus 2 root 5 over 16 divided by 2, 5 divided by 2, because this divided by 2 is 8. So we have 5 plus root 5 over 8, replacing this term here. So that's what we have here. Now this is x plus 1 minus root 5 over 4 squared plus 5 plus root 5 over 8. And that is progress. That is progress. We have our integral here. The integral from x tending negative infinity to x tending towards infinity of negative 1 over root 5 x plus 1 minus 1 over root 5 all over 2, all that over x plus 1 minus root 5 over 4 close bracket squared plus 5 plus root 5 over 8. So usually with such substitution, if you have something like, for example, 1, if you have 1 plus ax squared plus b, the trick is to say let x be equal to or let ax, let's assume this is also squared, so we'll say let x be equal to root of b tan theta, such that when you substitute in and you say let this also be squared, we have in place of ax we'll have b tan square theta plus b, right? so that you can pull b out the denominator and you have tan square theta plus 1, right? And so this becomes sec square theta, and since we have a dx there, then you're able to cancel that out. So we're going to now use this. We say x plus 1 minus root 5, this entire thing, be equal to the square root of b, which is 5 square root of 5 plus root 5 over 8 tangent theta, such that dx d theta is the same as still this constant 5 plus square root of 5 plus root 5 over 8 sec squared theta. And so dx now is the same as, or we can substitute for dx with root of 5 plus root 5 over 8 sec squared theta d theta. So this is our the variable what can be substituted for dx. Then looking at the limits here, as x tends to negative infinity, then from here, x tends to negative infinity, tan theta also tends negative infinity, and what that means is that the arctangent of that, theta tends to negative pi over 2. When x tends to positive infinity, tan theta also tends to positive infinity, and so theta, the arctangent of that, tends to pi over 2. So these are the new limits with the new substitution that we're going to involve here. The integral in x domain now can be transformed into the theta domain. So in place of x, we can substitute the square root of 5, the square root of 5 plus root 5 over 8 tan theta minus 1 minus root 5 over 4. And in place of x plus 1 minus root 5 over 4, we can substitute with square root of 5 plus root 5 over 8. Now that squared, we have 5 plus root 5 over 8 tan squared theta, and then this constant here remains, right? And the constant here also remains. And then in place of dx, we have the square root of 5 plus root 5 over 8 sec squared theta. So we can go ahead and pull this constant out, right? We pull it out, and we have tan square theta plus 1. And then we can pull this constant and this constant out. So we have square root of 5 plus root 5 over 8 over 5 plus root 5 over 8 out here. And then as you can see here, we have negative 1 over root 5, square root of 5 plus root 5 over 8 tan theta minus 1 minus root 5 over 4 close bracket plus 1 minus 1 over root 5 over 2. Now tan square theta plus 1 is the same as sec square theta, and we're going to see that this and that can cancel, but we'll see that in the next step. This is the integral we got in our last step, but we're quickly going to see that the sec squared theta term in the denominator, as we said previously, is going to cancel out with that, and then this division here, we're left with 1 over root 5, square root of 5 plus square root of 5 over 8 times the integral from theta equals to pi over 2 to theta equals to pi over 2, negative pi over 2 to positive pi over 2 of negative 1 over root 5 times this root square root of 5 plus root 5 over 8 tangent theta plus we multiply negative 1 over root 5 times this, so we get plus 1 minus root 5 over 4 plus 4 times root 5 plus 1 minus 1 over root 5 over 2. And we can do some quick math here. So 1 plus root 5 over 4 root 5 times 1, can multiply root 5 here, times root 5 in the numerator, such that we have root 5 minus 5 times 5 is 5, and then this is 4 times 5, which is root 5 minus 5 over 20, right? And then this here is the same as root 5 minus 1 over 2 root 5. And then multiplying root 5 in the denominator and in the numerator, we get 5 minus root 5 over 2 times 5, which is 5 minus root 5 over 10. So adding them together, we get 5 times root 5 over 10 plus 5 root 5, sorry, minus 5 over 20. And so common denominator 20 divided by 10, we have 10 minus 2 root 5 plus 5 minus 5. So we get 5 minus 5 here is 5 minus root 5 over 20, right? And so substitute here in place of this convoluted stuff here that we have here. So 5 minus root 5 over 20. So this is what we have here. Okay, we'll continue. We do have our integral. We have now 1 over square root of 5 plus root 5 over 8 times the integral from theta equals to negative pi over 2 to pi over 2 positive of negative 1 over root 5 times the square root of 5 plus root 5 over 8 tangent theta plus root 5 minus root 5 over 20. So tan theta let's just try to see. Tan theta is the same as sine theta over cos theta, which is the same as negative d derivative of cosine theta, of all over cos theta, such that the integral of tan theta is equals to negative natural log of cosine theta. Okay, so this is easily integratable. But we'll also look that if you're plotting tan theta from theta equals to negative pi over 2 to pi over 2, the curve is something like that, right? Symptotic about pi over 2, negative pi over 2. So this area here is under the curve, under the x-axis, the theta axis, and this area here, they're equal but opposite in sign. So the integral here is just 0, but we could also go ahead and show why that is 0 just with the limits. So once we have natural log cosine theta here at pi over 2 cosine theta is 0 and negative pi over 2 cosine theta is 0. So this is the same as limit as x tends to 0 of log x minus log x, right? Which is the same as limit as x tends to 0 of log x over x, which is equals limit as x tends to 0 of log of 1. So in other way, putting in these limits, this part here tends to 0. And then since we have theta here, this becomes this constant 1 over square root of 5 plus root 5 over 8 times 5 minus square root of 5 over 20 in bracket positive pi over 2 minus pi over 2, which becomes pi, as we see here. So that's where things have brought us. And so we do have our answer here, but let's try to express it such that we don't have this many integrals, just consolidating things. First of all, this 8 here can go up here, and we know that square root of 8 is the same as 2 square root of 2 times 4. Square root of 4 is 2, so this is the same as 2 root 2, right? And then so our expression here, we can simplify this further so that we have 2 root 2 over square root of 5 plus root 5, and then we have 5 minus root 5 over 20. Okay, so we can multiply the numerator and denominator with the same thing, and we choose to multiply with the square root of 5 plus root 5, right? But even before that, these 2 and the 20 divide, so we have 10. And then obviously multiplying both the numerator and the denominator by the same thing, we just want to remove the square root sign in the denominator. So we came up to here where we multiplied with the same thing, but now we are left with root 2 here. And since this multiplication here now results in now just 5 plus root 5 over in the denominator here. And then now we can also multiply with the conjugate, just trying to remove the, instead of plus here we have a negative here, so we're trying to remove the square root in the denominator. So this means that we have 5 root 5 minus root 5 squared, and that's the same as 30 minus 10 root 5. And then after this conjugate multiplication, we get 20. We see that this goes away, and then we multiply root 2 across, so 2 now goes into the root sign, so we have 10, and then we have 2 root 5 there. And here we have 3 minus root 5 times square root of 10 plus 2 root 5 over 20 pi. So this is what we get from the blue integral. Now we're going to go and try and look at the green integral, use the same steps to get the answer. Since our integral now involves blue and green, now we're going to focus on the green integral, and we'll use the same steps that we use in solving the blue integral. First, we want to create a perfect square involving the x term. And so how we do that is just the same way where we do x plus 1 plus root 5 over 4 squared, and then we subtract this square of this term here. And that can simplify into now the 1 minus the square of 1 plus root 5 over 4 simplifies into 5 minus root 5 over 8. So obviously getting our integral, the same very steps we use with the blue integral, we're just going to go ahead and now do the substitution, right? So we say let this part here, x plus 1 plus root 5 over 4 be equal to the square root of 5 minus root 5, square root of root 5 minus root 5 over 8 tan theta. And so dx d theta is the same as square root of 5 minus root 5 over 8 sec squared theta. So we can substitute dx with square root of 5 minus root 5 over 8 sec squared theta d theta. And then the limit, the same thing as x tends to infinity, theta tends to negative pi over 2. As x tends to positive infinity, theta tends to pi over 2. So going forward, we can now transform our equation from the x domain to the theta domain in a very similar manner we did previously. In place of x, we have square root of 5 minus root 5 over 8 tan theta minus 1 plus root 5 over 4. And so everything kind of takes shape here. We're able to pull 5 minus root 5 over 8 out, and so we're left with tan squared theta plus 1, and this is the same as sec squared theta. So we can also pull now this and this out. So we have square root of 5 minus root 5 over 8 over 5 minus root 5 over 8. And then denominator we have sec squared theta, and on this end also we have sec squared theta. So this and that can cancel. Going forward, the process continues. As we said, this and that cancel. Now, this divided by this, we have 1 over square root of 5 minus root 5 over 8 times the integral from theta equals to pi over 2 to pi over 2 of 1 over root 5. This time is positive, times square root of 5 minus root 5 over 8 tan theta minus obviously 1 over root 5 times 1 plus 5 over root 5 over 4 becomes now negative, this sign here, persisting 1 plus root 5 over 4 root 5 plus 1 plus 1 over root 5 over 2. Now this part here, we can simplify it further. That's the focus that we're going to work on, and so it becomes 5 plus root 5 over 20. Looking at the previous integral, we now know how tan theta evolves. Tan theta can be integrated to the natural log of cosine theta, and we already know that with the limits of negative pi over 2 and pi over 2, this here tends to 0. And so we are left with 5 plus root 5 over 20 theta, which when you include the limits, right? So pi over 2 minus pi over 2, this becomes pi, and then this constant. So we have 1 over square root of 5 minus root 5 over 8 times 5 plus square root of 5 over 20, and then this pi just comes here. So this constant comes from here. This comes from here right away. Okay, and do some further simplifications. Since we already have 1 over square root of 5 minus square root of 5 over 8 times 5 plus root 5 over 20 pi. This 8 here can go up, square root of 20 can go up, and we have, since we know square root of 8 is the same as 2 root 2, and then we have 2 root 2 over 5 square root of 5 minus 5 square root of 5. And the next thing we would want to do is we multiply both the numerator and denominator by square root of 5 plus root 5. And what that means is that even after cancelling with this, so that we have 10 here, we have square root of 2, 5 plus root 5, 10, and under the square root sign, we have square root of 20 because we found out that 5 plus root 5 times 5 minus root 5 is the same as 20. So we still have the square root sign there, and 20, square root of 20 is the same as square root of 4 times 5, and then square root of 2 is 2, so we have 2 root 5, right? And then we'll keep proceeding here. And so in place of square root of 20, we have 2 root 5. And so this 2 times 10 here becomes 20. And then we can multiply both the numerator and denominator by square root of 5. And then the square root of 2 multiplied across, this becomes 10, and this becomes 2 root 5. And so when you multiply 5, root 5, numerator and denominators, the denominator becomes 5, and then the numerator becomes here 5 root 5 plus 5 times square root of 10 plus 2 root 5. And so this 5 goes, and this becomes 1. So we have square root of 5 plus 1 over 20 times the square root of 20 plus 2 root 5 times pi, obviously. That is what is due to the green integral. So going further and combining the two integral, we already knew that the answer to the blue integral is 3 minus root 5 times square root of 10 plus 2 root 5 over 20 pi. And so the green is root 5 plus 1 over 20 times square root of 20. So we forgot pi here. This and that cancel, so we get 3 plus 1, which is 4 over 20 times square root of 10 plus 2 root 5. And so 5 divided by 4 here goes 1, divided by 4 here goes 5. And so the answer is now square root of 10 plus 2 root 5 over 5 times pi. And this is the final answer. So problem number 4 of the finals of the MIT 24 integration B is the definite integral from x equals to -1 over 3 to x equals to 1 of the cube root of 1 plus the square root of 1 minus x cubed plus the cube root of 1 minus the square root of 1 minus x cubed.
The solution to this problem, looking at the integrand, it has these two cube root components. And one thing I would do is just equate the integrand to y, such that when you take the cube of y, using binomial expansion, we'll have the cube of the first plus 3 times the first times the square of the second term plus 3 is equals 3 times the square of the first times the third, and then the cube. This is not square, the cube of the second term. And these are just binomial coefficient. For those of you who are familiar with Pascal triangle, you could use that to obtain these binomial coefficients. So what this results to is the power 3 here negates the cube root sign on the first and the last term here, such that when you look at this, this term here is equivalent to this term, but the signs are opposite, so this and that would cancel out. And then here, we can now pull out 3 and also the product of the first and the second term here, so that what you're left with is the sum of the first and the second term, which means that this component is just y. So we have 2 plus 3 times the first and the second term times y. Now, as you can see, we can combine this cube root sign, and so you have the product of the sum and the difference, which means that this is the same as the square of the first and the second minus the second term. So now we have 2 plus 3 cube root of 1 minus, because we have multiplied this together, the square of the square root of 1 minus s cubed. So when you take into consideration the square under the cube root sign and also taking into consideration the square root under the square sign, what happens is now we have 2 plus 3 times cube root of 1 minus 1 plus x cubed, and this 1 and that cancel out, so we're left with the cube, the square, the cube of x, and cube root of the cube of x is just x, so we have y cube is equals to 2 plus 3xy. Now what that means is that now if we differentiate 3y squared dy dx is equals to, the 2 is a constant, so that's a 0, plus differentiate with respect to x, we have 3y, plus with respect to y, so we have 3x dy dx. And that means that when we now take this component to this opposite side, and then you divide both sides by 3y squared minus 3x, we get that dy dx is 3y over 3y squared minus 3x. And then now what that means is that 3y squared minus 3x over 3y dy is the same as dx. So we would like to express this x in terms of y. Here what happens is you just 3x is the same as y cubed minus 2 over y, yeah, is equals to 3x. So we can substitute for this 3x with these components. So we get now 3y squared minus y cubed minus 2 over y, all over 3y. And so what that means is that we have 3y cubed minus y cubed, in bracket y cubed minus 2 over 3y squared. And so that means that now we have 2y cubed plus 2 over 3y squared dy can be substituted for the dx in the integration. Now, since y is equal to the cube root of 1 plus the square root of 1 minus x squared cubed plus the cube root of 1 minus square root of 1 minus x cubed. And we've also found that y cubed is equal to 2 plus 3x y. So when x is equal to a third, when you insert a negative a third here, we get y cubed is equal to 2 minus y. And so that means when you take everything on the right to the left, that means that y cubed plus y minus 2 equals to 0. So a very quick trivial solution is when y is equals to 1, when y is equals to 1, that equation holds, right? And then the next thing, we also know that when x equals to 1, we can substitute in 1, and what we find out is that y is equals to 2. So the lower limit is y is equals to 1, and the upper limit y is equals to 2, right? And so our integration now becomes the integration from y is equals to 1 to y is equals to 2 of y, which comes in place of this complicated expression, times dx. dx now here we found to be 2y cubed plus 2 over 3y squared. And we see that this y cancels with that, and we're left with the 2/3 comes out, and so the integral from y equals to 1 to 2 of y squared, because we pull out the these 2's, and then 1 over y. So eventually now what we have now is 2/3 the integration of from y is equals to 1 to 2 of y squared plus 1 over y. And we know that the integration of y squared is y cubed over 3, and the integration of 1 over y is natural logarithm of y. And so substituting in the limits, that amounts to 2 over 3 for the first component. This is 2 cubed over 3, which is 8 over 3, minus 1 cube over 3, which is a third, plus log 2 minus log 1. So this one here, as we know, tends to 0. Natural logarithm of 1 or log of any base of number 1 is 0. And then we're left with now 8 over 3 minus a third is 7 over 3 plus log 2. And then if you multiply a third across, that becomes 14 over 9 plus 2 over 3 log 2. And this is the answer of that problem number 4.
Problem number 5 of the finals of MIT 24 integration B is the integration from x equals to 0 to x equals to 1 of the maximum of the expression for which the integer n being integers greater than 0 of 1 over to the power n open brackets of the floor function of 2 to the power nx minus floor function of 2 to the power nx minus a quarter. It's a very interesting problem.
What I'd like to do first of all is to explain what a floor function is. A floor function is a function that extracts the integer lower than any real number that you give it to. So for example, if we're looking at floor function of x, that is equals to integer k when x lies between when x is greater or equal to k or less than k plus 1. As soon as x is equal to k plus 1, this value shifts to k plus 1, and so on. Then the floor function of 2x is equals to k when 2x is between the integers k and k plus 1. As soon as 2x becomes k plus 1, this becomes k plus 1. But so long as 2x is greater or equal to k and less than k plus 1, then the floor function of 2x is equals to k. So in that event, that means that x should be greater or equal to k over 2 and less than k plus 1 over 2. So if we were to plot this, it means that when x is between 0 and 1, the floor function of x is 0, and when it hits 1, it changes to 1, and it stays there until x is 2, and when it becomes 2, it transitions quickly to 2. And that is what a floor function does. Now, if you to consider the floor function of 2x, so because 2x becomes 1 at a half, that means that from 0 to a half, we have 0 as the floor function of x, and as soon as we reach half, it becomes 1, and it becomes 1 up to 1, and that when x equals to 1, we have 2 times x, or 2 times 1 being equal to 2, and so it transitions to 2, and then it stays at 2 until we get until 1 under 1.5, and then at x equals 1.5, it transitions to 3, and so on. And that also would happen if we have a floor function of 4x. At a quarter is where it becomes 1, and then it stays there up till a half, and at a half, half times 4, we get 2, it stays at 2 until 3/4, and it transitions to 3, and then at 1, it becomes 4, and so on. So that is what a floor function does. Now, that's what I just described. Now, for our problem, we have, let's begin by looking at the floor function of 2 to the power n x minus the floor function of 2 to the power n x minus a quarter. So when n equals to 0, what happens is that we have x, floor function of x, minus the floor function of x minus a quarter. So if we have our graph like this, it means that from 0 to 1, 0, and then from 1 to 2 it becomes 1, and then from 2 to 3 it becomes 2. Now, x, flow function of x minus a quarter. So first of all, from 0 to a quarter, from 0 to a quarter, this expression is negative a quarter. So the integer lower than negative a quarter is negative 1. As soon as we hit a quarter, this expression becomes 0. And then from there onwards, everything is 0 until 1 and a quarter. That's where now it transitions to 1. And it continues to be 1 until we are at 2 and a quarter. That's where now it transitions to 2 and so on. So you see that we do have a lag here, we do have a lag here, and we do have a lag here. Now the difference between the flow function of x and the flow function of x minus a quarter at this point, from 0 to a quarter, will be 1. And then from 1 and 1 and a quarter, the difference will be 1. Otherwise, all the other places will have 0. And then between 2 and 2 and a quarter, the difference will also be 1. So we are only having these 1 intervals from 0 to a quarter, and from 1 and 1 and a quarter, from 2 and 2 and a quarter. So this only happens when the function is transitioning to the next integer. So because of the lag that exists between these two functions, you have a difference of 1 for the duration where the two functions are not equal. So for n equals to 2, n equals to 1, sorry, we have the flow function of 2x minus the flow function of 2x minus a quarter. So what that means is that for the flow function of 2x, from 0 to a half, it's 0. From a half to 1, it's 1. From 1 to 1 and a half is 2. And then from 1 and a half to 2 is 3. And then for the flow function of 2x minus a quarter, again, we have that lag comes in, but the transition now happens at x equals to 8, because at x equals to 8 is when now 2x becomes a quarter, and this becomes 0. So the lag happens for only 1 over 8. And so you see it happens at the transition, that's at 0, and then at a half, and then at 1 and 1 and a half. So those transitions where the function 2x is changing its value is where you have this lag, and therefore at 0 to 1 over 8 you have this difference being 1 for the duration of an eighth, and then from a half to a half plus an eighth, you have another difference over eighth, and then from 1 to 1 plus an eighth is where you have the difference over eighth, and so on and so on. So as you see here, what happens is when you increase the value of n from 0 upwards, 1, the number of these difference points increases, but also the width also decreases. But the difference remains to be 1. So we're having these rectangles with a width of changing from a quarter when n is equal to 0. It changes to an eighth when n is equal to 1. When n equals to 2, it changes to 1 over 16, but the height remains to be 1. So that is what this expression is all about. Now, for our problem, choosing the maximum, we have to do a little bit more. So looking at n equals to 0, we saw that in that between 0 and 1, when x equals to 0 to x equals to 1, we had only the transition or the lag existing for a quarter, and that's when that difference was 1. In other regions, it was 0. When n was equals to 1, we saw that the lag existed at 2 points between x equals 0 and 1. That was at 0, x equals to 0. And then when x equals to a quarter, and so we have these rectangles, these two locations. When n equals to 2, we expect it to be at 0, but the width being now 1 over 16 will be at 0, at a quarter, at a half, and at 3/4. When n equals to 3, we expect to have the lag existing at x equals to 0, at x equals to an eighth, at x equals to 2/8, x equals to 3/8, x equals to 4/8, which is a half, 5/8, 6/8, 7/8, right? And so that is how the progression goes. And then when n is equals to 4, we expect it to be the transition to be at x equals to 1 over 16, 2 over 16, 3 over 16, 4 over 16, and so on. So the next thing now is to now consider this factor of 1 over 2n, right? To the power n. So what this means is that as n increases, because we have this factor, the entire value here decreases, even if the difference is 1. So our choice should be that as long as there is for whatever region from x equals to 0 to 1, the lower the integer n, the higher or the more maximum the value is. So it makes more sense because from n is equals to 0, the factor is 1 over to the power 0, which is 1. Here we are multiplying by 1 over to the power 1, which is a half. Here we are multiplying by a quarter. Here we're multiplying by 8th, and here we're multiplying by 16th. So definitely in this region where we have a difference, this is the maximum. And because we've already chosen here, in the next subregion, we will ignore this and consider here, because here between a half and 5 over 8, because there is no value when n equals to 0, this becomes the maximum. And going on, when n equals to 2, because we've already chosen this to be our maximum value, we will only go and say, okay, this will be maximum in this region because there's no other candidate here. And we cannot choose this because we've already chosen this region or this to be our maximum. But here, because there's no prior value here, we will choose this. The same will happen here. We cannot choose this, we cannot choose this, we cannot choose this, but we can choose this because this is the only candidate with nothing in the lower values of n. We'll choose this, we won't choose this, we will choose this, we will choose this. So there are three candidates there. And then with here, we won't choose anything here. We will choose this, we will choose this, we won't choose this, we won't choose this. we won't choose this. I mean, we'll choose this. We will not choose, we probably will choose this, and we'll choose this. So that's how you go about choosing the regions that give you the maximum value for that specific interval. So essentially what happens is for n equals to 0, this is what we'll choose, what is in red here. For n equals to 1, we'll choose this. For n equals to 2, we'll only choose this and this. For n equals to 3, we choose this and this and this. So we have 3 points that we'll choose. And then for n equals to 4, we'll choose this, this, and this, and this, and this. So we'll choose 5 rectangles. And so as we can summarize, for n equals to 0, the choice is 1 rectangle. For n equals to 1, there's only 1 rectangle. For n equals to 2, we're choosing 2 rectangles. For n equals to 3, we are choosing 3 rectangles. For n is equals to 4, we are choosing 5 rectangles. Now, there's definitely a series that, or a pattern we're seeing here. If you see here, this first one is the same as 0 plus 1, we get this. And this here is the same as this 1 plus this 1. Okay? This 3 here is the same as 1 plus 2 goes to 3. And this 5 here is the same as 2 plus 3 being equal to 5. And in succeeding ends, we'll have to follow that sequence. And this is what we call the Fibonacci sequence. It is a very famous sequence in mathematics and computer science. So knowing that, our integral therefore is, what we'll do is, it's for n equals to 1, we know that constant is 1 over 2 to the power 0. And then the rectangle is of width a quarter, and the height is 1. And then there's only 1 rectangle. And then for n equals to 1, the constant is 1 over 2 to the power 1. And then the width of the rectangle is 1 over 8 times 1. And then there is only 1 rectangle to be considered. When n is equals to 2, 1 over 2 to the power 2, the width of the rectangle is a 16th. And then the height is 1. And there are 2 rectangles to be considered. When n equals to 3 is 1 over 2 to the power 3, the width of the rectangle is 1 over 32, and then the height is 1, and then there are 3 rectangles to be considered. And when n equals to 4 is 1 over 2 to the power 4 as the constant, the width of the rectangle is 1 over 64 times half, which is the height, and then there are 5 rectangles, and we continue so on and so on and so on. So what this results is 1 over 2 to the power 0 is 1 over 1, which is 1. But now we're left with the quarter here. 1 over 2 times 1 over 8 is 1 over 16. 1 over 4 times 1 over 16 is 1. It's times 2 is 2 over 64. 1 over 8 times 32 is 256. Times 3 is 3 over 256. 1 over 16 times 1 over 64 is 1 over 1024 times 5 is 5 over 1024. So this is the same as 1 over 4 to the power 1, 1 over 4 to the power 2, 1 over 2 to the power 4 to the power 3, 2 over 4 to the power 3, 3 over 4 to the power 4, 5 over 4 to the power 5. And then this constant here, as we've said, the Fibonacci elements, so members of the Fibonacci sequence. So this is F1. We've omitted F0, so we have F1, we have F2, we have F3, F4, F5. For F0 is 0. So the important thing to know is that a Fibonacci sequence, before we go there, we can just quickly express this as the summation from k equals to 1 of the kth value of the Fibonacci sequence over 4 to the power k. The Fibonacci element, or the kth element, can be expressed using this golden ratio, but I mean, you can go and do some research. The kth value is 1 plus root 5 to the power k minus 1 minus root 5 to the power k over to the power k times 5th. So we can simplify to say that this is 1 plus root 5 over 2 to the power k minus 1 minus root 5 over 2 to the power k over root 5. So we can put these in place of fk so that our integral is now the summation from k equals to 1 to infinity, or 1 plus root 5 over 2 to the power k minus 1 minus root 5 over 2 to the power k over root 5 over 4 to the power k. Now, I can pull this 4 into this expression and here, and then pull this outside here. Okay, that constant. So we do have a 1 over root 5, and we have 1 over 2. So let's pull this 4 in. So we have 1 plus root 5 over 8 minus 1 minus, or to the power k, minus 1 minus root 5 over 8 to the power k. So this is a geometric series. The initial value will be this to the power 1. So we have 1 over root 5 with the initial value being 1 plus root 5 over 8. And then the denominator is 1 minus the common ratio, which is 1 plus root 5 over 8. The same thing for the second one. So as we can see, we can now get the common denominator here, and this becomes 8 minus 1 minus root 5. And the 8 cancel out, so we have 1 plus root 5 over 7 minus root 5 minus 1 minus root 5 over 7 plus root 5. And then when you multiply the denominators, so because this is the product of the difference and the sum, we have 7 squared minus root 5 squared, which is 5. And then this divided by this, the product divided by this times this is just a 1 plus root 5 times 7 plus root 5 minus 1 root 5 times 7 minus root 5. So 1 times 1 plus root 5 is 7 plus 5. And then 5 times 7 plus root 5 is 7 root 5 plus 5 times 5, which is 5. The same thing happens here. So we have to, because this is plus, so we are adding 5 here. So as you can see, this cancels with this, and then this cancels with this. Now we are left with 8 root 5 minus minus, which is now plus another 8 root 5. So we do have 16 root 5 over 44, because 7 squared is 49 minus 5. And then since this cancels with this, and then 16 divided by 44 by 4 goes 4. And then by 4 becomes 11. So our final answer is 4 by 11. And this is the answer to this problem. So it's certainly a very interesting problem.
So on to the tiebreaker problems. So tiebreaker problem number 1 of the MIT 24 integration B finals, which is the indeterminate integral of 1 over the 4th root of x to the power 4 plus 1.
Problem for me when I do see a plus and x to the power something. A quick substitution that I think about is tangent substitution. And so I say let x squared be equal to tan theta, such that 2x dx d theta equals to sec squared theta, and therefore dx equals to sec squared theta over 2x d theta. And so since x is the square root of tangent theta, so we have dx be equal to sec squared theta over 2 root square root of tan theta d theta. And so 1 over the fourth root of x to the power 4 plus 1 dx is equals to this integral of 1 over fourth root of tan squared theta plus 1 over sec squared over 2 square root of tan theta, which now, since tan squared theta is the same as sec squared theta, we have now half this 2 pulled out of the square root of 1 over fourth root of sec squared theta times the sec squared theta over square root of tan theta. Fourth root of sec squared theta is the same as the square root of sec theta. So going forward, we have half of the integral of 1 over square root of sec theta times sec squared theta over square root of tan theta. And so tan theta can be expressed as sine theta over cosine theta, which means that it's the same as the square root of sine theta times the square root of sec theta. So therefore, since we have 2 square roots, sec theta square root sec theta square root is the same as sec theta. So we are left in the numerator with sec theta. So what we have here is half of the integral of 1 over sec theta times sec squared theta over square root of sine theta. So this divided by this results into half times the integral of sec theta over square root of sine theta. So sec theta is the same as 1 over cosine theta. So we have here the integral of 1 over cosine theta square root of sine theta. Now we want to eliminate the square root sign. We say let u be equal to sine theta. Therefore, du d theta is the same as cosine theta. We apologize for this mistake. And so du is the same as cosine theta d theta. And du over cosine theta is the same as d theta. And what that means is du over square root of 1 sine squared theta is equal to d theta. And sine squared theta is the same as u squared. So du over square root of 1 minus u squared is the same as d theta. So this integral here becomes 1 over 2 integral of 1 over square root of 1 minus sine squared theta in place of cosine theta, and then we have sine theta here, and we forgot to include d theta here. Okay. So this means that in place of cosine theta, we have 1 minus sine squared theta, which is 1 minus u squared. In place of sine theta, we have u. In place of d theta, we have du over square root 1 minus u squared. So these times this results into 1 minus u squared, and we're left with square root of u there. And so let y be equal to square root of u. Therefore, y squared is the same as u. 2y du is equals to 1, and therefore 2y dy is equals to d. So this integral here now becomes half the integral of 1 over 1 minus y to the power 4 in place of y squared, and then y in place of root of u, and then in place of du we have 2y dy. And so this y and this cancel, and okay, this one and this will cancel out. And so we're left with the integral of 1 over y to the power 4, which is an easy integral because now we can use integration by, not integration by parts, but we can use partial fractions. So we can split this in form of 1 minus y squared, the denominator, in form of 1 minus y squared and y plus y squared. So expressing that into partial fractions, we have half the integral of 1 over 1 minus y squared plus 1 over 1 plus y squared. And so we can split this first integral further, and the 1 over 1 minus y squared is the same as half of 1 minus y plus 1 over 1 plus y, and then that half times the half that was already there, this becomes a quarter, the integral of 1 over 1 minus y plus 1 over 1 plus y. And then this next integral remains half the integral of 1 over 1 plus y squared. So quick thing, this is the same as a negative a quarter, natural logarithm of 1 minus y, the integral of 1 over 1 minus y. And then this is the same as a quarter, natural logarithm of 1 plus y. And then this is a very famous integral, which is now half times the arctangent of y. Now, since y is equal to square root of u, we just plug in the square root of u there. We can swap this positive and negative, and so we have 1 over natural logarithm of 1 plus square root of u minus 1 over 4 times natural logarithm of 1 minus square root of u plus half arctangent of square root of u. So that is that, and also since u is equal to sine theta, we can plug sine theta in place of u, and that's what we get. But again, since x squared is equal to tangent of theta, that means that if we have a right angle triangle like that, and then we have the base angle be theta, then tangent of that theta is the opposite over the adjacent, which is now x squared, and that being opposite and then adjacent is 1, and the hypotenuse is x squared plus 1 squared, which is just 1. Therefore, sine theta being opposite over the hypotenuse is sine theta is x squared over the square root of x squared plus 1. So therefore, our final integral of 1 over the 4th root of x squared, x to the power 4 plus 1 is equal to a quarter natural logarithm of 1 plus, in place of sine theta, we have square root of x squared over the square root of x squared plus 1. And in place of the sine theta, we've done the same. In place of the sine theta, we've done the same. So the next thing is we can express this as a common base, and therefore square root becomes root the power 4. And so here we have 4th root of x squared plus 1 plus x minus a quarter. This is also 4th root. We apologize for that mistake. And so we have a quarter natural logarithm of 4th root of x squared plus 1 plus x over 4th root of x squared plus 1 minus a quarter of 4th root, a natural logarithm of 4th root of x squared plus 1 minus x over 4th root of x squared plus 1 plus arctangent of x over the 4th root of x squared plus 1. This is, we apologize for that mistake. And so the final answer is the same as 4th root natural logarithm, quarter times natural logarithm of the 4th root of x squared plus 1 plus x over the 4th root of x squared plus 1 minus x plus half arctangent of x over the 4th root of x squared plus 1. So this is our final answer. In the final answer provided, they swapped, so you could also express it as half arctangent x over 4th root of x squared plus 1 plus a quarter natural logarithm of 4th root of x squared plus 1 plus x over the 4th root of x squared plus 1 minus x. Same answer, but this was the answer that was provided. We apologize for the errors there, but all the same, you get to understand how this problem could have been solved.
So tiebreaker number 2 of the MIT 24 integration B is the definite integral from x equals to 0 to x equals to 2 pi of open bracket sine 2x minus 5 sine x close bracket times sine x all over cosine 2x minus 10 cosine x plus 13.
To the solution to this problem, I think the quickest thing to do is just express everything into the single angle formalism, because we do have the double angle expressions, sine 2x and cosine 2x. So we could simplify this further. Sine 2x is 2 sine x cosine x. And then cosine 2x is cosine squared x minus sine squared x, which is 2 cosine squared x minus 1. So when you multiply sine x across, this becomes 2 sine squared x cosine x minus 5 sine squared x over, in place of cosine 2x, we have 2 cosine squared x minus 1 minus 10 cosine x plus 13. So that can be simplified further by re-expressing sine squared x in form of cosine squared x, which is 1 minus cosine squared x. And similarly, this sine squared x also has been expressed in terms of 1 minus cosine squared x. So simplifying that further, in the numerator, we have minus 2 cosine cube x plus 5 cosine squared x plus 2 cosine x minus 5 over 2 cosine squared x minus 10 cosine x plus 12, because it's negative 1 and the 13 interact to yield 12 here. So which is good. We can decide to pull this negative out. And so we have 2 cosine cube x minus 5 cosine squared x minus 2 cosine x plus 5 over cosine squared x minus 10 cosine x plus 2, with the negative sign outside the integral sign. So this is an improper fraction. Why? Because the numerator is greater than the denominator. So we can take advantage of long division. So we say 2 cosine cube x minus 5 cosine squared x minus 2 cosine x plus 5 divided by 2 cosine squared x minus 10 cosine x plus 12. So if you multiply the divisor by cosine x, we get 2 cosine cube x minus 10 cosine squared x plus 12. Then you subtract that from the dividend, and you get 5 cosine squared x minus 14 cosine x plus 5. And then if you multiply the divisor by, if you multiply that by 5 over 2, we get 5 cosine squared x minus 14 cosine x. Sorry, we get 5 cosine squared x minus 25 cosine x plus 30. And then when you subtract that from the difference that we got previously, we get 11 cosine x minus 25. So what that means is the negative integral of 2 cosine cube x minus 5 cosine squared x minus 2 cosine x plus 5 over 2 cosine squared x minus 10 cosine x plus 12 is negative. The integral of cosine x plus 5 over 2 minus the integral of 11 negative, 11 cosine x minus 25 over 2 cosine x minus 10 cosine x plus 12. Since whatever we have in the numerator here is the remainder from the long division. So it's easy to see this, because since our interval is 0 to 2 pi, since cosine x swings in both the positive and negative direction in equal measure, it's easy to see that cosine x after integration goes to 0. But we'll do our due diligence and show that, yeah, indeed it is 0. So we can also go about by factorizing the denominator, and that becomes 2 cosine x minus 4 times cosine x minus 3. So integrating this first part, cosine x becomes sine x, 5 over 2 becomes 5 over 2x. Then we have 0 to 2 pi as our interval. So what happens here is that with sine x sine 2 pi minus sine 0, with 5 over 2x is 5 over 2 times 2 pi minus 5 over 2, 0. And so sine of 2 pi is 0, sine of 0 is 0. And 5 over 2 times 2 pi, the 2's cancel, so we get 5 pi, but we have a negative sign there, so it becomes negative 5 pi. Now, focusing on the next part here, this we can decompose this fraction into partial fractions, and that becomes 4 over cosine x minus 3 plus 3 over 2 cosine x minus 4. Now, we can say let t be equal to tangent of x over 2, such that dt dx is a half of sec squared x over 2. And so 2 dt over sec squared x over 2 is equals to dx. And we know that sec squared x over 2 is 1 plus tan squared x over 2. So 2 dt over 1 plus t squared is equals to dx, right? And so looking at our integral, this is the same as negative 5 pi minus the integral from x equals to 0 to pi of 4 over cosine x is the same as cosine squared x over 2 minus sine squared x over 2 minus 3. And then since we had 2 cosine x, the same thing happens here. Now, since t equals to tangent x over 2, if we have a right angle triangle and the base angle there is x over 2, and since the tangent of x over 2 is t, and we know that tangent of an angle is the opposite over the adjacent, so t is the same as t over 1, so our opposite would be t, and then the adjacent would be 1, and the hypotenuse therefore would be the square of the two sides, so square root, which is now square root of t squared plus 1. And therefore, cosine x over 2, which is adjacent over the hypotenuse, would be 1 over square root of t squared. And then the sine of the x over 2 would be t over square root of t squared plus 1. And so therefore, this integral here becomes negative 5 minus. And one thing to note here is that the limits would tend to negative pi, a negative infinity to positive infinity. I'd like to explain why that is the case. So if you have a graph, right, and this is our 0, and then we have pi, right, and then you plot, okay, let's say this is 2 pi, right, and then this is 4 pi. So, and here we have pi. So if we're plotting tangent x over 2, essentially our asymptote will be at pi because that's when x over 2 at this point is pi over 2. And so, and then at negative pi, we'll have another asymptote. So we'd have a curve like that, right? And then the same thing would happen here. We would have something like that. Right? So since we are interested in integrating from 0 to 2 pi, the behavior here is very similar to the behavior here. Right? And so we can pretty much consider the behavior between pi and 2 pi to be similar to the behavior of our, because we're looking at t behaving, so this is tangent x over 2. Right? And this is t, right? So t being tangent of x over 2, as x approaches pi, it tends to positive infinity, right? And then on the lower side, on the upper side of pi, it tends to negative infinity. And then at 2 pi, it's 0. And that is the same behavior here. So we can say our integral essentially is from t equals to negative infinity, or tending to negative infinity, to t tending to positive infinity. And that's why now we have added our limits as shown here, right? And then in place of cosine squared x over 2, we have, since we have cosine squared x over 2, we have 1 over square root of t squared plus 1 squared, so 1 over t squared plus 1. And then sine squared x over 2 is t squared over t squared plus 1 minus 3. And the same thing happens here, but we have a 2 here. So simplifying that further, here in the denominator, having a common denominator of t squared plus 1, and then that flipping to the numerator. And since in place of dx, we had 2 dt 1 plus t squared, and we see that this one here cancels with this and with this, right? And so as we go ahead, we see that we have 4 over negative, we have these 2 here coming all the way out. And then we have 4 over negative 2 minus 4t squared. And as if we have a negative here, multiplying it across, that becomes a positive. Same here, we have 4 over 2t squared plus 1. And then we have 3 over 2t squared plus 1 for this integral. We can now deal with this blue integral and the green integral separately. With the blue integral, we can just say let t equals to 1 over square root of 2 tan theta, so that dt d theta is equals to 1 over square root of 2 sec squared theta. And so dt is the same as 1 over square root of 2 sec squared theta d theta. And when t tends to negative infinity, theta tends to negative pi over 2. And when t tends to positive infinity, theta tends to pi over 2. So substituting in for t with 1 over square root of 2 tan theta, we get 4 over square root of 2 from here and here, and over 1 over, since this squares and this 2 becomes 2, the square root of 2 becomes 2, the 2's cancel. So we are left with essentially 4 over root 2, 1 over tan squared theta plus 1 times sec squared theta. And so tan squared theta plus 1 is sec squared theta. The sec squared theta is cancelled out. So this one and that one cancel out. And we are left with 4 over root 2, integral from theta equals to pi over 2 to pi over 2 of the theta. That integral essentially is just theta with, sorry, this is, let's use it negative. And so we have 4 over square root of 2 pi, because pi over 2 minus pi over 2 becomes pi. And multiplying the denominator with root 2, numerator and root 2, we have 4 root 2 over 2, so we have 2 root 2 pi as the answer for the blue integral. The green integral, we can let t be equals to 1 over root 3 tan theta, such that dt d theta is 1 over root 3 sec squared theta. And so essentially dt is equals to 1 over root 3 sec squared theta d theta. And then when t tends to infinity, negative infinity, theta tends to pi over 2. When t tends to infinity, theta tends to positive pi over 2. And so the integration simplifies to outside we have a constant of 3 over root 3, and then integral of d theta of 1 from pi over 2 to pi over, from negative pi over 2 to pi over 2. So that is 3 over root 3 pi, and multiplying root 3 to the denominator and the numerator. The denominator becomes 3, and then we have the 3 and the numerator and denominator cancel, so we have root 3 pi. And this is the answer for the green integral. So since our question demanded that we have negative 5 pi plus the blue integral and the green integral, we know the blue integral resulted into 2 root 2 pi, and then this green resulted into root 3 pi. The answer is essentially 2 root 2 plus root 3 minus 5 pi. That is the answer that was provided in
Number 3 of the MIT 2020 Integration B finals is the indefinite integral of the square root of x to the power 4 minus 4x plus 3.
into the solution. The first thing with this problem is you just want to try to factorize whatever is inside the square root sign. And by long division, you soon understand that it is whatever is under the square root sign is x minus 1 squared times x squared plus 2x plus 3, right? And then you can pull out the x minus 1. That is now giving us x minus 1 times the square root of x squared plus 2x plus 3 as the integrand. The next thing now you could do is express this as a perfect square. So first thing you want to do is you look at 2 here, and that means that it derives from x plus 1 squared. And now you can remove the product, subtract the product, which is minus 1, but keep this constant here, there. So you are left with x minus 1 times the square root of x plus 1 squared plus 2 as our integrand. Now, how to remove what the square root sign is, we have other ways we could do it, but what quickly comes to mind to me is just use the substitution of tangent theta, and because we have this plus sign here. And obviously, you have to equate x plus 1 to square root of 2 tan theta, so that when you square this part, this entire constant can be taken out, and you're left with tan squared theta plus 1, which reduces to sec squared theta. So as I said, let x plus 1 be equal to square root of tan theta. Therefore, dx d theta is square root of sec squared theta, and therefore dx is square root 2 sec squared theta d theta. So our indefinite integral now becomes substituting for x plus 1 with square root of 2 tan theta. This part here, x minus 1, therefore from here, as you can see, x is equal to square root of tan theta minus 1, and then minus 1, so it becomes square root of 2 tan theta minus 2. And then the bracket in the square root sign, square root of tan theta squared plus 2. And as you can see, when you square the square root of 2 here, it becomes 2, and then pull that out, and you get root 2 as the constant. Okay, and then for dx, we have square root of 2 sec squared theta d theta. As you can see, this and that multiply with each other, and we can take this out here as 2, right? And tan squared theta plus 1 is sec squared theta, square root of sec squared theta is sec theta. sec theta times sec squared theta becomes sec cubed theta. And we have put our 2 here as needed. So going forward, we have 2 times the integral of into bracket square root of 2 tan theta minus 2 times sec cubed theta. Multiply sec cubed theta across, so we have square root of 2 under the integral sign times sec cubed theta tan theta. And then now we have 2 times this 2, we have minus 4 the integral of sec cubed theta. Now, the green integral is tricky. When we differentiate tan x times sec x, we get 2 sec cubed x minus sec x, such that a half, when you add this both sides, a half of the derivative of tangent, the product of tangent x and sec x plus sec x is equals to sec cube x. So we can now plug this part here. And so we have our integral as 2 times the integral of square root of sec cube theta tan theta minus 2 the integral of the derivative of tan theta sec theta close bracket plus sec theta. So this one here is very easy to see. Sec cube theta tan theta, that derivative is a third sec cube theta. And then here, when you integrate that, it just becomes tan theta sec theta. And then we're left with this as our other problem. So as I said, this part here, when integrated, becomes a third sec cube theta, and then we have 2 times root 2, so we have 2 root 2 over 3 sec cube theta. And here we have an obvious problem, which is minus 2 tan theta sec theta, because this is already derivative, so when you integrate, you get whatever is under the derivative or the differentiation sign. Now we are left with minus 2 the integral of sec theta. Could have kept this blue. But let's continue. This is the same as 1 over cosine theta, and then we can express it as the half in the half angle formalism, so which is 1 over cosine squared theta over 2 minus sin squared theta over 2. Okay, and then since we have the difference of 2 squares, this can also be expressed as the product of the difference of those 2 numbers and the sum of the same numbers. We can express this as partial fractions, and believe you me, this is a very simple partial fraction. This is the same as cosine theta over 2 plus sine theta over 2 over cosine theta over 2 minus sine theta over 2 plus cosine theta over 2 minus sine theta over 2 over cosine theta over 2 plus sine theta over 2. And then we integrate this. You can see the numerator here is the numerator is the derivative of the denominator, right? And the same thing happens here. So for example, cosine, when you differentiate cosine theta over 2, this becomes minus sine theta over 2. When you differentiate sine theta over 2, it becomes positive cosine theta over 2. Obviously, there is a half here, and that's why these 2 disappeared. The same thing here, when you differentiate cosine theta over 2, you get minus cosine, you get minus sine theta over 2. When you differentiate negative sine theta over 2, you get negative cosine theta over 2. So there will be a negative sign here to negate whatever negative was created here. So as you can see, we are left with now minus now
because we are now integrating this, since the numerator is the same as the derivative of the denominator, and the half is not there from the differentiation, we assume there is a constant 2 that was initially applied there. So we have now 2 log of this, and since we had a minus here, since we had a minus here, we're going to keep a negative sign there. Okay. And so we can continue, and eventually we are left with this. And here, this is very easy because of the rules of logarithm. If you have a subtraction of the log functions, this is the same as division within the log function. And so the next thing we may want to do is just express this back into the single angle formalism. So we multiply both the numerator and denominator by cosine theta over 2 plus sine theta over 2. And that becomes cosine squared theta over 2 plus sine squared theta over 2 plus 2 sine theta over 2 sine cosine theta over 2 sine theta over 2. So this here tends to 1, the popular identity, and then this obviously is sine theta. Right? And here this is same as cosine theta. So our problem now becomes root 2 root 2 over 3 sec cube theta minus 2 tan theta sec theta minus 2 logarithm of 1 plus sine theta over cosine theta. And since x plus 1 is equal to root 2 tan theta, what that means is that tan theta is the same as x plus 1 over root 2. And if you have a right angle triangle there with the angle theta, since the opposite tangent of that angle is opposite over adjacent, our opposite here can be considered to be x plus 1. And then our adjacent is root 2, and therefore the hypotenuse is x plus 1 squared plus 2. And so sine theta is the opposite over the hypotenuse, which is x plus 1 over square root of x squared plus 2x plus 3. And cosine theta is the same as the adjacent root 2 over hypotenuse, which is x squared plus 2x plus 3, right? And so substituting back for sec square cube theta, this is the same as 1 over cosine cube theta, and then 2 tan theta, sec theta is the same as 2 sine theta over cosine square theta, minus log 1 plus sine theta over cosine theta. So for cosine theta, there we do have root 2 over the square root of x squared plus 2x plus 1, and then we cube that denominator, and then 2 times 1 over cosine square theta, that is 1 over root 2 over square root of x squared plus 2x plus 3 squared times sine theta, which is x plus 1 over root square root of x squared plus 2x plus 3, minus 2 log 1 plus sine theta is x plus 1 over square root of x squared plus 2x plus 3, and then cosine is root 2 over x squared, square root of x squared plus 2x plus 3. So this can be simplified further because this can now go up, and since we're cubing it, this is the same as 2 root 2 over 3 times, since square root of 2 cubed is 2 root 2, and you see that this and that will cancel. And since this flips back, and since this becomes 2 over x squared plus 2x plus 2 plus 3, sorry, to the power 3 over 2. And then here we have this x plus 1. And then since there's a 2 here, there's 2 times x plus 1 times, this is, when you square this, this becomes x squared plus 2x plus 3. But since we have the root here, so we are left with the square root of x squared plus 2x plus 3. And this 2 and this 2 cancel. The same thing goes on under the natural logarithm sign.
And so we have square root of 2x squared plus 2x plus 3 as our common base, and then we add square root of x squared plus 2x plus 3 and x plus 1. And since this and that cancel, so we are left with whatever we see here over square root of 2. So as we can see, we have a third times x squared plus 2x plus 2 to the power 3 over 2 minus x plus 1 times square root of x squared plus 2x plus 3 minus natural logarithm of x squared plus 2x plus 3 plus x plus 1. And since we have this under here, this can be separated into a separate log. Since there's a negative here, this becomes plus log of square root of 2 to the power this 2. And since this is just a constant, this is just part of the bigger integration constant, our answer is third times x squared plus 2x plus 2 over 3 to the power 2 minus x plus 1 times the square root of x squared plus 2x plus 3. So this was supposed to be 3. Keep it as 2. This is 3. Sorry for that mistake. But yeah, and then minus 2 natural logarithm into bracket square root of x squared plus 2x plus 3 plus x plus 1 plus the integration constant. And this is the answer.
So the tiebreaker number 4 of the MIT 2024 integration finals is the definite integral from x equals to or equal x tending negative infinity to x tending to positive infinity of sine squared of 2x to the power x times cosine squared of 3 the power x, open brackets, 4 cosine squared 2x, open another bracket, 4 cosine squared 3x minus 3 close bracket squared minus 1. That's very, very interesting problem.
Problem is, as I said, quite intricate. The first thing that I would personally do is look at the innermost bracket, and there we have a combination of 4 cosine squared 3 to the power x minus 3. What is interesting here is we could play around with that, and then so if we multiply cosine of 3 to the power x into this denominator, and then obviously have a denominator of cosine 3 to the power x as follows. You realize that we have 4 cosine cube 3 to the power x minus 3 cosine 3 to the power x over cosine 3 to the power x, because we multiply both the numerator and the denominator by cosine 3 to the power x. So the numerator here, for those of you who know the expansion of cosine 3x, it gives us, and here x is essentially 3 to the power x. So what that means is that in the numerator, we do have, in place of 4 cosine cubed 3 to the power x minus 3 cosine 3 to the power x, we have cosine 3 times 3 to the power x. And then in the denominator, we still have the cosine 3 to the power x. Now let's shift our focus now to the green part. That green portion can also be expressed by multiplying the denominator by sine squared to the power 2x. If we do that, here we've just opened up the bracket by squaring both the numerator and denominator. But if we multiply the green part both to the numerator and denominator with with sine squared 2 to the power x, what that essentially becomes is we have the square of sine 2 times 2 to the power 2x. right? So we've made the numerator that, since sine 2x is 2 sine x cosine x, so when you square that, that becomes 4. And so that's 4 sine x cosine x, and that's the same thing that we've done with x being 2 to the power x in that regard. So what that means is now we can keep the denominator as it is, and the numerator can now be simplified as sine 2 times 2 to the power x, all that squared. Okay. And the denominator obviously just remains like that. But as you can see, this and this can cancel with this when you multiply with whatever is outside the bracket. And then you're left with the numerator only when we multiply by this component that is outside the bracket. So that now leads to, we have now the integral from x equals to negative infinity to positive infinity of sine squared 2 times 2x times cosine squared 3 times 3x minus, because we have this 1 here, this entire thing remains. So you're minus sine squared 2x times cosine squared 3x. So we can simplify this further. Since the bases here are the same, we have sine squared 2 to the power x plus 1 times cosine squared 3x plus to the power 3, the cosine squared 3 to the power x plus 1 minus sine squared 2x times cosine squared 3x. If you look at these two functions, they are pretty similar, only that in the first component here, or the first term, x has been replaced with x plus 1. So if we say if fx is the same as sine squared 2 to the power x times cosine squared 3 to the power x, then what we can see is that our integral here, which is the same as that complicated integral we're given at the beginning, is the same as the integral from x equals to negative infinity to positive infinity of f of x plus 1 minus of fx, since this is fx, right? Now, one interesting thing is with this integral, when x tends to negative infinity, 2 to the power x tends to 0, 3 to the power x tends to 0, 2 to the power x, and so on, tends to 0. So this entire thing just collapses to 0. And that is a very, very important thing to, first of all, have in mind. So when x tends to negative infinity, 2 to the power x tends to 0, and also 3 to the power x tends to 0, right? So fx being equal to sine squared 2 to the power x cosine squared 2 3 to the power x tends to 0, since sine squared 0 is just 0. So this tends to 0. And also, let's continue. So what that means is that I here, being the integral of this, can be considered to be the integral from x equals to infinity to x equals to positive infinity of fx plus 1 minus fx. And then the integral from x equals to infinity to x equals to a is equals to the separate integral of this fx plus 1 from negative infinity to a minus the integral of fx from x equals to infinity to a. Since we know at negative infinity, or as x tends negative infinity, these integrals tend to 0. And what that means is that the integral IA, which is the integral from x equals to infinity to positive to a, becomes the integral of fx plus 1 minus the integral of fx. And if we let x prime be equal to x plus 1, then the x prime is the same as dx, meaning that we can insert x prime in place of x plus 1, but with the limits, the lower limit still remains negative infinity. The upper limit becomes a plus 1. So this integral here still becomes, we can just replace everything back with x. So the integral of fx plus 1 is the same as the integral of fx from negative infinity to a plus 1. And what that means is that we can now expand this such that we have the integral from infinity, negative infinity to a plus the integral from a to a plus 1 minus this component that is still there. So you realize that this and that can cancel out, and our integral IA remains the integral from a to a plus 1 of fx. But notice our original integral is the limit of a tending to infinity of IA, I being equal to the integral from x equals negative infinity to positive infinity of fx plus 1 plus minus fx is the same as the limit of a tending to infinity of the integral from x equals to negative infinity to a of x plus 1 minus fx. But we've now realized that this IA is the same as the integral of fx plus from x equals to infinity, a to a plus 1, with a tending to infinity, therefore, meaning that this expression is the same as our original expression, I. Now, we know what fx is. Fx is sine squared to the power x times cosine squared 3 to the power x. We can express that into a double angle formalism by removing the squared. So sine squared 2 to the power x is the same as 1 minus cosine. 2 times 2 to the power x over 2. Cosine squared 3 to the power x is the same as cosine 2 to the power x plus 1 over 2. Now, when you multiply that, we get a quarter times cosine 2 to the power 2 times 3 to the power x plus 1 minus cosine 2 times 2 to the power x times cosine 2 times 3 to the power x minus cosine 2 times 2 to the power x. And we can isolate this 1 here and then play around with these terms, the extra terms we've gotten. But you realize that with this constant here of 1, when you integrate that, you get x, and then applying the limits appropriately, we are left with just a quarter times 1. But the important thing here is that as a tends to infinity, these other remaining terms, we have the lower limit being positive infinity and the upper limit being positive infinity, right? So this a quarter plus a quarter, the integral from infinity to infinity of this cosine terms here implies that this entire thing just tends to 0 because there is no interval. The interval is limited to infinity. And so this entire terms here tend to 0, the entire integral. And so our answer remains to be a quarter. And that is the answer.
Tiebreaker number 5 of the MI for integration B finals is definite integral from x equals to 2 to x and to positive infinity of the floor function of x times x squared over x to the power 6 minus 1.
And first thing that one would like to do is to understand the concept of flow function. What is a flow function? So a flow function basically is a discretization function that coughs out the integer lower than the real number that you feed in. So for example, if x is a real number, the flow function of x is k if x is greater or equal to k and less than k plus 1. As soon as x hits k plus 1, the flow function of x becomes k plus 1. And then it continues being k plus 1 until x becomes k plus 2. And that's when, again, the flow function becomes k plus 2, and so on and so on and so on. So in terms of just expressing it in a visual way. So if we have a x and y coordinate like that, and we have a flow function of x, we see that from x equals to 0 to x equals to 1, we have x being equal to 0. And as soon as x hits 1, there's a quick transition to 1, and then that stays at 1 until x equals to 2. That's when now the flow function now shifts to 2. So that is what a flow function really does. Now, for our problem here, if we have the integral from x equals to 2 to infinity of the flow function of x times x squared over x to the power 6 minus 1, that's the same as the integral from 2 to 3, when at that point the flow function is 2, so 2x squared over x to the power 6 minus 1, plus the integral from 3 to 4. In that interval, the flow function is 3, so 3x squared x to the power 6 minus 1, plus the integral from 4 to 5. In that interval, the flow function is 4, and so on and so on. So the general way of expressing that is the summation from k equals to 2 to infinity of the integral from k to k plus 1 of k x squared over x to the power 6 minus 1. Now, one thing we could do is we just let u be equal to x to the power 3, such that du dx equals to 3x squared. And so du over 3x squared is equals to dx. And so du over 3 to the power u to the power over 3 times u to the power 2 over 3 is also equal to dx. And so by substituting for dx with u, we have now the summation from k equals to 2 to infinity of k. And since u is equivalent to k to the power 3, x to the power 3, the lower limit now becomes k to the power 3, and the upper limit becomes k plus 1 to the power 3. And in place of, so we pull this k out of the integral sign, but in place of x squared, we have u to the power 2 over 3. In place of x to the power 6, we have u to the power, u squared minus 1. And then in place of dx, we have du over 3u to the power 2 over 3. So this u to the power 2 over 3 would cancel out. And we're left with a simple integral of these 3 comes out. We're left with the summation from k equals to 2 to infinity of k over 3. The integral from k cubed to k plus 1 cubed of 1 over u to the power. So the u squared minus 1 is our integrand. So quick thing, we can now express the 1 over u squared minus 1 into partial fraction. That's the same as 1 over u minus 1 minus 1 over u plus 1. As you can see, that's the same as when you integrate that, we get natural logarithm of u minus 1 minus natural logarithm of u plus 1. And then the limits apply appropriately. So I also forgot to tell you that obviously when you express it in this partial fraction format, you have to multiply by constant over half, and half multiplied by k over 3 becomes now k over 6. So substituting in, substituting, but inserting in the limits, we have, in place of u, we have k plus 1 cubed minus 1, and then we have lower limit k cubed minus 1. And then obviously for this second term, k plus 1 cube plus 1, and so on. So here we're left with k over 6. And then using the rules of logarithms, we see that where we have subtraction becomes division. So we have k plus 1 cube minus 1 divided by k cube minus 1. And then because when we apply a bracket here, this becomes a plus. So this now becomes a numerator. So we have k cube plus 1 over k plus 1 cube plus 1. So as simple as that. Now, we can go ahead and now expand it out. So from when k equals to 2, we have 2 over 6 log. Here we have 3 cube minus 1. Here we have 2 cube plus 1, 2 cube minus 1, 3 cube plus 1, plus k equals to 3 over 6, and so on and so on. Now, one thing we could also do is we can pull out a sixth and then apply the power, push out the numerator as powers into the log function. So we'll pull out 1 over 6, and then we still have 2 log 3 cubed minus 1 times 2 to the power 3 plus 1 over 2 to the power 3 minus 1 times 3 plus 1 to the power 3 to the power 3 plus 1 plus 3 log, and continuing so on and so on. Now, when we now push out these powers up like that, we have these terms here being squared for when k equals to 2, and then this term becomes cube. But what we know is that when we have this summation of the log function, that's the same as the multiplication of the terms that are within the log function. So by doing that, we can now just multiply everything together. And as you can see, these 2 here would cancel and leave this as 1. And this would cancel, leaving this as 1. So essentially what that does is very interesting. So we are left with just the initial term, which is 2 to the power 3 plus 1 squared over 2 to the power 3 minus 1 squared times 3 cubed plus 1 over 3 cubed minus 1, 4 cubed plus 1 over 4 cubed minus 1, and so on and so on. So the thing we could also express is now we can remove 1 because there are 2 here, there's square here, and obviously 2 cubed plus 1 is 8 plus 1, which is 9. 2 cubed minus 1 is the same as 8 minus 1, which is 7. And then you have this product sign from k equals to 2 to infinity of k cubed plus 1 over k cubed minus 1. So next thing is, this is obviously 1 over 6 times natural logarithm of 9 over 7. The limit as n tends to infinity of the product from k equals to 2 to n of k cubed plus 1 over k cubed minus 1. So this is very interesting. This is where things really begin to be very, very interesting. This product here can be simplified as follows. So since we have k cubed plus 1 over k cubed minus 1 multiplied n times, when you factorize k cubed plus 1, that's k plus 1 times k squared minus k plus 1 over k minus 1 times k squared plus k plus 1. And then since this is just a product, we can now multiply this separately. So we have the product from k equals to n of k plus 1 over k minus 1 times the product of n from k equals to 2 to n of k squared minus k plus 1 over k squared plus k plus 1. And so this is the same as, just multiplying the numerator separately from the denominator. So product of k plus 1 from k equals 2 to n over the product from k equals to 2 to n of k minus 1 times the product. And now this can be simplified as k minus 1 squared plus k minus 1 plus 1. And then this denominator just remains as it is. If we adjust the index by saying k prime is equal to k plus 1, that means that k prime at the lower part here becomes 3, and this just becomes k prime. So we can say this is the same as just the summation from k equals to 3 to n plus 1 of k over the summation. Here, if we again say k prime is equal to k minus 1, that means the lower bound becomes k equals to 1, and the upper bound becomes n minus 1. So we just adjusted that appropriately. And here again, same thing, k prime equals to k plus 1. The lower index becomes k plus 1. And then everything, the numerator and denominator become the same. So what we see here, the numerator and denominator are exactly the same, only that the numerator here starts from 3 to n plus 1, and the denominator here starts from 1 2. So we have something akin to the numerator, we have 3 times 4 times 5, up to n times n plus 1. And in the denominator, we have 1 times 2 times 3 all the way up to n minus 1. And we can see that all these cancel up to here. And now we have n times n plus 1 over 2 remaining. Same thing here. This begins from 1 all the way to n minus 1. The denominator begins from 2 all the way to n. So what we have is the missing part here is the denominator misses 1. And so in the numerator, we have 1 squared plus 1 plus 1. And the numerator misses the nth part over n squared plus n plus 1. So essentially, that becomes that, as shown here, which is equals to 3n, because there is 3 here, 1 plus 1 plus 1, 3. And then here we have n times n plus 1. So we have n times n plus 1. And the denominator we have, we have a 2 that needs to be there. There's 2 here. And then there is the n squared plus n plus 1. So 2 times n squared plus n plus 1. So this is the product of k cubed plus 1 over k cubed minus 1 up to n. So we can now just bring this here, and that is 1 over 6 natural logarithm of 9 over 7, limit of n tending to infinity of 3n times n plus 1 over 2 times n squared plus n plus 1. Very interesting. So if we divide the numerator and the denominator by n squared, what happens is we are left with 1 over 6 natural logarithm of 9 over 7, limit of n tending to infinity of 3 times 1 over 3 times 1 plus 1 over n over 2 times 1 plus 1 over n plus 1 over n squared. So this tends to 0 when n tends to infinity. This tends to 0. And this tends to 0, right? And so we are left with 3 times 1 and 2 times 1 here, which is 3 over 2. So we have 1 over 6 natural logarithm of 9 over 7 times 3 over 2, which is a 6 natural logarithm of 9 times 3 is 27, 7 times 2 is 14. And this, my friends, is the answer that we're looking for.
On to the lightning round, problem number 1 of the MI 2024 integration B finals, the integration from x equals 0 to x equals to 1, or open this giant brackets of open brackets again, 1 minus x to the power 3 over 2, close bracket to the power 3 over 2, minus, open another bracket, 1 minus x to the power 2 over 3 to the power 2 over 3. So these powers on the second bracket are similar to what you have on the first bracket but flipped.
So this problem, as I said, is super interesting. What personally I would do is to separate this into 2 separate integrals. So the first integral, I would color it as blue, which is the integral from x equals 0 to 1 of 1 minus x to the power 3 over 2 all to the power 3 over 2 minus the integral from x equals 0 to 1 in bracket 1 minus x to the power 2 over 3 close bracket 2 over 3. And this last would, just use color coding to separate these 2 integrals. So with the first integral, the first thing I would do is I would let u be equal to the integrand, which is 1 minus x to the power 3 over 2 to the power 3 over 2. And so if I got the cube root on both sides, now I have u to the power 1 over 3 equals to 1 minus x to the power 3 over 2 all to the power a half. And then if I square both sides, now I have u to the power 2 over 3, which equals to now 1 minus x to the power 3 over 2. Now I can subtract u on both sides and add u to the power 2 over 3 on both sides, and then add x to the power 3 over 2 on both sides. And now I have 1 minus u to the power 2 over 3 equals to x to the power 3 over 2. And then get the cube root on both sides, and then square both sides. And now we have x being equal to open bracket 1 minus u to the power 2 over 3 to the power 2 over 3. So essentially, the small change, or d, of 1 minus u to the power 2 over 3 or the power 2 over 3 is the same as dx. And also when x equals to 0, u is equals to 1 minus 0 to the power 3 over 2, which means that u is 1. And then when x is equals to 1, then u is equal to 0. So our integral now, the blue integral of 1 minus x to the power 3 over 2 all the power 3 over 2 is the same as, since we equated this part to u, this is u, small u, and then dx is this part. Now we have an integral that's very interesting, but also the limits, we've flipped it because that's what you demanded us to. But now we have integration by parts, where we have u, and then we have this part, d1 minus u to the power 2 over 3 to the power 2 over 3. And using this integration by parts, if you have the product of u and dv, then we have that resulting into uv minus the integral of v du. So our dv is this, and our u is this small u. So now integrating that, uv is u times 1 minus u to the power 2 over 3, all the power 2 over 3, and applying our limits appropriately. Sorry, this is 0, this is not u. Minus the same integral from 1 to 0. And now, since our v is 1 minus u to the power 2 over 3, all the power 2 over 3, and then du is our d small u, right? So when u is 0, this entire thing goes to 0 because this u is 0. When u is 1, this is 1, and so 1 minus 1 is 0. So this entire thing is going to 0. So this entire expression is 0. And now we are left with negative the integral from u equals to 1 to 0, or 1 minus u to the power 2 over 3, all to the power 2 over 3. Because of this negative sign, we can flip the limits. So now we have the integral from u equals to 0 to 1 of 1 minus 2 to the power 2 over 3, all to the power 2 over 3. Now, with this integral now, you can change u to x, and what we're seeing here is that our integral from x equals to 0 to 1 of 1 minus x to the power 3 over 2, all the power 3 over 2 is equal to the integral of from x equals to 0 to 1 of 1 minus x to the power 2 over 3 from this, right, to the power 2 over 3. So our original problem now, since there's this equality here, means that if we're subtracting this integral from this integral, that means that the final answer is 0, because the integral of this is the same as the integral of this. And so the final answer just collapses to 0.
Round number 2 of the MIT 2024 integration B finals is the indefinite integral of open bracket x over x minus 1 close bracket to the power 4.
Of this problem, so the first thing that I would do is just say let u be equal to x minus 1, because why? I don't really like having this extended format in the denominator. So what then that results to is du dx is equals to 1, and therefore if you to go on with the substitution, you can replace dx with du if you replace x with u. And so the integral now becomes the integral of in place of x, since x is u plus 1, we have u plus 1 to the power 4, and the denominator x minus 1 is u to the power 4, and in place of dx we have du. Now what is u plus 1 to the power 4? We can use Pascal's triangle. 1, if it's this power is 1, we just go with 1, and if you have two items to the power 1, we have just 1 and 1, and then if you have a square, and then the quotients are 1, 2, and 1, and if we're talking about power 3 here, we have 1, 3, and 3, and 1, and if we are looking at 4, we have 1, 4, 6, 3, and 1, and this just comes from adding the successive numbers in the upper row. So what we can now get from u plus 1 to the power 4 is, for the quotient 1 is u to the power 4, quotient 4 is 4 to the times u to the power 3 times 1 to the power 1, and since 1 to any power is 1, we'll remove the 1 component, we'll just not bother about that, and then 6 times u to the power 2, sorry, this is 4 here. I should have paid more attention. It's not working. My pen is not working. 4. Okay, this is 4u and then 1. Then we divide through by u to the power 4. That results to 1, 4 over u. 6 over u squared, 4 over u to the power 3, and 1 to u to the power 4. So going forward now, trying to integrate these independent terms independently. For 1, it's u, 4 over u is 4 log u, and 6 over u squared is minus 6 over u. And then for 4 over u to the power 3, we have minus 4 over 2 u squared. And then for 1 over u to the power 4, we have minus 1 over 3 u cubed. Now, since we can continue working with this so that we have 2 here, simplify the numerators, and since we know that u is equals to x minus 1, we'll just substitute in where we see u with x minus 1, and this is what we get, plus obviously c, which is our integration constant. Now it's just a little bit uncool to have a constant here, another constant here, so we can bunch this constant with this c here, and so we have x plus 4 log x minus 1 minus 6 over x minus 1 minus 2 over x minus 1 squared minus 1 over 3 times x minus 1 cubed, and then plus the new integration constant. And this is the answer that was provided.
Last problem of the lightning round problems of MIT 24 integration B finals is the integral, indefinite integral of open bracket tangent of 1012x plus tangent of 1013x close bracket times cosine 1012x times cosine 1013x all over cosine 2025x.
The thing I would do with this problem is just simply look at expanding the tangent part of the problem. So I'll just label it as the blue component here, and what this is essentially is I'll pull out the denominator, and then this is sine 1012x over cosine 1012x, and then sine 1013x over cosine 1013x close bracket. And then, as you can see, we can get a common denominator, which is the product of the cosines here, which obviously is the same as the green component here, which could end up cancelling out. And then the numerator now becomes sine 1012x times the cosine 1013x plus sine 1013x times cosine 1012x. So as you can see here, this part here and this would cancel out, and eventually we get sine 2025x, this one here, and then denominator would be cosine 2025x. As you can see, the numerator is the negative derivative of the denominator, obviously with this constant applied, 1 over 2025. So the integral of this problem is essentially negative natural logarithm of 2025x over 2025, and this is the answer. Very simple. I think the contestants should have arrived at it very, very fast. Thank you very much. Until next time, bye-bye.